Hi, everyone. Thanks for joining my session about why most AI agents never scale and how you can build the ones that do. My name is Vadim Briliantov. I'm a technical lead of Koog, and some of you might remember that exactly 1 year ago, on the same KotlinConf, on the same stage, I have presented Koog, the Kotlin AI agent framework. And I also promised that the year 2025 will be the year of agentic AI. Please raise your hand if you actually noticed lots of new AI agents coming up at the news. Great. So indeed, lots of new startups, experiments, demos, and definitely hype. But what about this year? Well, I think that this year, 2026, will be the year when AI agents would finally enter production. And we have to be prepared, right? So let's take a look at the retrospective for the Koog framework, where we have been so far. So as I said, May 2025, 22nd, exactly 1 year ago, we have released the first version of Koog. Later on, we also added persistence so that Koog agents can also be durable and fault-tolerant. Then we also integrated with different observability tooling so that you can also monitor and debug your running agents. Later on, at the beginning of this year, on the latest Java one, we actually also presented Koog for Java. So please don't forget to tell about that to your Java colleagues. They have to be also happy about that. Then, 1 month ago, on the Spring I/O, we also launched full Spring Boot and Spring AI integrations for Koog. And the last thing is we just launched the local model on-device support for Koog so that you can run agents on Android devices even without the internet. All of that means that so far, Koog has matured. But today is a very special day for Koog. And I want to take a moment here on the stage to say happy birthday, because Koog turns 1 year. And as you probably already know from the keynote, any birthday is not like really a birthday without presents, and we also have one which is our 1.0 release. Isn't it the best way to celebrate the birthday of the framework, right? And now let's get back to the actual question. Why most AI agents never scale? Well, you probably expect that I would just tell you and answer this question, but let's first ask Koog itself. We've just built a demo local Android and iOS app, which is called Ask Koog. And it can tell something about the KotlinConf, Kotlin, AI, and Koog, of course. So, hey Koog, tell me why most AI agents never scale. So, most AI agents never scale because they are built in Python. That's a good one. But tech stack and platform choices do matter once your cute demo agents meet real users. And you know what? I would agree. Indeed, you have to build agents where your enterprise already lives, whether it's JVM, JavaScript, Android, iOS, or WebAssembly. You don't have to switch the stack. But that's not just it. Agents don't just scale because you build them in different platforms. And there are other reasons. So if you ask me, but not the AI, why most AI agents never scale, I would also tell you that, well, in real scenarios, you need control. And you probably know that there's been a lot of hype about the AGI and these magical black boxes that just work and can solve any possible problem on Earth. But the hype is almost over. You probably noticed that even OpenAI recently released the Agent Kit so that you can build specialized agent workflows. So naive prompting never work in real system, and you can never trust them. You have to be able to control what your agent is doing. Next thing is, well, money. Who loves money? I love money. We all love money. And I'm pretty sure that many companies also love to earn money and to not spend too much money, right? And that's especially true when you're building AI applications because, well, they come with a cost. Moreover, there are context limits for most of the models, and it's pretty easy to hit them. And if you do, your agent doesn't work. You cannot just deploy it to production and be sure that it's not going to let you down. Last but not least, as I already told during the keynote, agents are long-running processes and that they might fail, and you have to be able to recover from any crashes. Otherwise, you cannot call them scalable. So, the plan for today is we're going to build a simple agent, and that's it. Well, of course, no. We're also going to develop the tools, integrate into a backend. It's going to be a Spring backend, but you can also integrate it with any other backend. Then we're going to let our agents remember the previous conversations. Why? Because they are not just demos in a Python or Jupyter or Kotlin notebook. They are real systems. They need to be able to interact with the users and remember everything about the previous conversations. And then we're going to solve the first problem of the scalability, which is no control. We're going to add control to our agents. Then we're going to also solve the second problem and make them fault tolerant. We're going to also integrate with monitoring tools. And last but not least, we're going to solve the money problem. So let's go. Let's build a simple agent with Koog. Just a brief technical introduction. So what is an agent? An agent is actually a three-component system. It's, of course, the agent itself, the environment, and models, one or many. From the user's perspective, of course, it's very simple black box. The user would just click a button or send a request and get back the response. Pretty simple, right? But under the hood, the whole process is happening. So the agent will be calling models, and the models will be coming back with model responses that are either assistant messages or tool calls. If the model decides to call a tool, then the agent will go to your environment, actually call the tool, and come back with the tool result. But that's not it. The process will continue again and again and again until the strategy powering the logic of your agent will decide to stop. And that's only when your user will see the final result. Until then, the agent is still working. Any ideas? What's the environment for you if you're building a Kotlin backend or mobile application? It's actually your Kotlin application. It's going to be the environment for your agent. The agent will be calling tools from your app. And to build a simple agent in Koog, you just have to explain the picture on the left with the code on the right. First, register the tools from your app. We're going to go through that. Second, optionally define a strategy, the controllable logic for your agent. Then configure the agent to work with a specific model to execute a specific prompt and provide any other limitations and parameter like maximum iterations, for example. And of course, we have to connect to models. For example, OpenAI, Anthropic, Ollama, Mistral, whatever models you prefer, one or many. And that's it. So if you want to build a simple banking backend, and that's, by the way, what we're going to be building today, it's pretty easy. Just AI agent, tool registry, or register my banking tools. Your banking assistant, that's going to be the system prompt. I'm going to work with GPT 5.4 Pro, just because I want. And connect to OpenAI prompt executor. That's it. 1, 2, 3, 4 lines of code, and your banking application becomes instantly agentic. And you don't even need to provide a strategy. And that's amazing, great, perfect, agentic demo, not the real app. But you can run it. You can ask the agent to send $100 to Mike, and probably the agent will call some tools like sending money in your banking app, get your account, get Mike's account, and Mike will be $100 richer. Hopefully, if it works. And it will during the demo. And by the way, no RPC is required. You don't need MCP to connect to some other external service. Banking tools are the tools from your current Kotlin app that you are developing, and the agent is working just right there in your Kotlin app. So we just built a very simple agent. And now we are ready to develop tools in Kotlin. So let's do that. Let's ask Koog, how can I develop tools? And it will tell you. The tools are basically any Kotlin functions or method, and you just have to put a tool annotation on top. And also, optionally, you can explain what the tool is doing to the LLM using another description. So let's do that. But first, we have to understand that, well, you define the methods, the model will construct the arguments. You cannot control that. You don't know what will be provided. And you have to also write lots of checks so that the tools are not unreliable. But you can control the outputs and the logic for the tools because you are the developer, while the model will control the order of the execution. And that's very important because that's true only if you don't provide a strategy. You might think that the banking agent will first get the list of contacts and then send it to the Mike, the $100. But maybe no, maybe it will not get the list of contacts and just send $100 to some random other person. So let's develop tools. Let's say that I have a send email function in Kotlin in my banking app with 2 parameters. How to make it a tool? Just call it a tool. Pretty easy, right? But what is the format for the email, and what does it return? Even human cannot guess just from the signature of the function. So you have to explain to the human or to the model. You can optionally provide descriptions. And now it's clear that it sends email and gets the reply. And the email is, well, just the email. But you can develop much more tools. Let's connect our agent with your backend. So the agent will be able to read something from the database, and for that we're going to define a toolset, account reading tools. Toolset is just a marker interface from Koog. You just have to inherit any class from it, and that's it. And inside you can define the methods. But first, remember that I told you that, well, agents will construct all the arguments for you. Do you want the agent to use some other account, not yours? Well, probably it's not reliable enough. All the secrets, user IDs, any sensitive information should never be exposed to the model. You have to inject it from your application so that you control that. And the model will just see that. Start date, status, and other arguments, but not the user ID. So I'm going to define the tools like the agent will be able to get the latest transactions, account balance, and account information. But that's boring. We don't want to build yet just another child support. We want our agents to be productive and proactive so that they can help the user to fix the problem for them, not just explain the problem. So let's connect to the writing tools. So the agent will be able to initiate a dispute about the transaction, cancel transaction, and even transfer money. So far, agent can do anything. It can do the conversation, reads, and writes. And that's how we develop the tools. And then we're going to explore what's the problem with that. But now let's first integrate it with your backend, with Spring. So for that, instead of manually defining the connections to OpenAI or Anthropic, I'm going to use Spring Boot integration. You just open your Spring Boot config and define AI Koog OpenAI, AI Koog Anthropic keys, and that's it. Or you can also use Spring AI integrations just with the different keys. And then prompt executor, this is the abstraction from Koog. It will be injected as a bin. And then you can actually build the agent. Just create one and launch it. And you can notice that there is a second parameter in the run function. Apart from the question, we also provide the user session ID. Because the agent might work in parallel with different users, and it needs to be able to keep track of all the sessions. So there is a parameter for that. Now let's define the first API method. For that, I'm going to define the API controller that has our Koog agent service and /support endpoint for our agent. It's going to get the principal for authorization with the user and the user's request. Then it's going to launch the support agent and come back with a response once ready. No worries, it's a suspend function. It will recover some time and come back with a response. Pretty easy, right? But there's a problem. How your agent can remember what was before? What if the user comes back and asks to follow up? For example, like I ask, send $100 to Mike, and then send again the next day. What's again? To whom? What to do? So it has to remember the previous conversation. Let's enable that. The good news is AI agent instance is not single use. It remembers the session. But what if your application restarts on another machine? For that, you need chat memory that will dump all the agent memory into a database. Let's do that. Pretty easy. Just install a feature. Please raise your hand if you know anything about Ktor. Cool. So you probably know that in Ktor you can install features into HTTP server. It's kind of the same concept here. If you don't know, this is just a way of doing dependency injection. It will intercept different places of the agent's execution and perform different actions. So in this case, after the agent has finished, it will dump all the state into the storage that you can provide by yourself. And of course, you don't want to pollute your database or S3 storage with too many messages. So for that, there are filters and size windows. You can also play with that. Well, chat history provider is a primitive interface, just store and load. But usually you don't need to implement one because there is Postgres via exposed integration, MySQL, all of that is available. You just connect to your database and it will store it in a table. But if you're using Spring, it's even simpler. You can use Spring Boot data source integration, connect to your JDBC Postgres endpoint, and from the Spring AI, we just get chat memory repository, and it will wrap it into Koog's chat memory history provider. That's it. That's how it works. That's the bin from Spring AI, and you just install it to your agent. That's it. Now let's take a look how it works. I'm asking, send $100 to Mike. And it says failed. I continue the conversation the next day, come back to the same endpoint and say, why? And it says, because you only have $99. You're not as rich. Want to send less? Yes, I do, $20. And it does it for me. That's chat memory in action. But that's not it. Even if your agent is not single use, it's not yet scalable. And now we are hitting the first problem. You don't have control over all the operations. Let's analyze our agent. So far, we have connected our agents with many different tools. It can do the conversation, read from the database, write to the database, and so far, LLM model will rule everything, all of the operations in your banking system. Is that really what you want? Well, probably no. So there are obviously some problems. And the most essential ones is that, well, all these randomly working guessing machines, I love that one, if you give too much control, they will mess up your system. The problem is actually in this default strategy that we never talked about before. That's how it works. You just start your agent, it asks the LLM what to do, LLM comes back with a tool call, you call a tool, and then you continue the process until LLMs decide to finish. No control, no focus, no limits, no guardrails. That almost would never work in real productions at scale. And by the way, you can also implement this strategy. That's actually Koog code. You can do that. It's doing a while true loop, almost. But, well, it doesn't work, except demos. So the problem is, well, first of all tools are available at once. And if you give too much control and too many tools, LLM will be just distracted with the amount of information and with the freedom. Moreover, you cannot just specify any guardrails except you prompt them. And if you prompt the guardrails, there is no guarantee that the models will follow the prompt. I mean, of course, you can hope, but that's it. To solve this problem, you have to define a custom specialized strategy. And we're going to use domain modeling approach for that, which is, by the way, a gift from the JVM and from Kotlin, because you can not do that with untyped languages. So the idea that we have to understand is the idea of subtasks. They are almost like sub-agents, like smaller ones, focused on a subset of tools and a smaller task, not the whole one. But the difference between the subtask and sub-agent is that sub-agent work independently. It doesn't know anything around it. It doesn't remember what was in the agent before it. But subtask is a part of a workflow. It is integrated and it shares the context and the conversation with everything that has been before. Importantly, it also has strictly typed input and strictly typed output. And under the hood, it can call many tools in a loop. So essentially, instead of describing the expected output as a text, you can describe what you want as the output data class, like that. That's what I want from this step. I need account number, username, related transaction ID, dispute ID if relevant, and so on. Everything is strictly typed, and it's also described for the model. And of course, it has to be serializable. Importantly, instead of just guessing from the prompt what you want, you are defining the form that the model has to fill. If you think of that from the real-world analogy perspective, imagine that you are coming to a bank, and you're applying for a loan. And, well, you cannot impress a banking manager with your oratory skills. You cannot talk your way into getting a loan. You have to bring your passport, your certificate, your salary documents, and all of that, and then fill in the form. And if you don't bring your passport, if you forget that, or if you don't fill the form correctly, it will not be able to get a loan. And even if you try to break through the system, probably the security guard in a bank will stop you. So essentially, Koog serves this security guard kind of purpose. It makes sure that the agent is not allowed to proceed further to the next subtask until the form is filled in. So let's illustrate that. The agent comes in and it's required to fill in the account issue summary form. And it starts calling the tools. It gets the account info and fills in, account number and the username. Not enough. It has to proceed further. Gets account balance and fills in the balance. I'm so rich. Cool. Then, not enough. It needs the information about the transactions. And it gets the related transaction ID, and dispute ID is null. No dispute has been initiated so far. And that's when the form is filled in. And only now, the agent is allowed to proceed further to the next step of the workflow. So even for the agent, sometimes a little bit of bureaucracy is a good thing, especially when in Germany. To sum it up, naive prompting gives you only hope, but the domain modeling approach gives you a contract that you can trust. And now, with all that knowledge in mind, let's finally develop a custom strategy for our banking assistant. For that, let's start with the first node. It's called start, and it's going to get us the user's question, what the agent needs to do. It's going to be a string. Then the first subtask will be identify the problem, with only access to conversation tools and account reading tools. No modifications is allowed. And I'm requesting my agent to fill in account issue summary form with all the details about the problem. And only after the form is filled in, then it can proceed further to fixing the problem step. That's going to be focused on another part of the subtask, and it's going to get only the access to database reads and database writes. No user conversations are required here. And I'm asking to provide me with the account issue solution with some other fields. So, are we done yet? We just identified the problem and fixed the problem. Well, Probably as developers, you never just commit untested code to master, right? Do you? Raise your hand if you do that. OK, I also do that. But usually we have to verify. We have to check that the account issue solution is actually correct. And for that, I'm going to add a verify solution step that will take the account issue solution. And by the way, please notice that I can only connect the steps that are type compatible. The previous one gets me account issue solution, and the next step takes the account issue solution. Otherwise, the code will not compile, and I will show it to you. And this step will produce a critic result. That's a standard class from Koog. It has 3 fields: whether verification was successful, optional feedback, what has to be improved, and the input, which in our case is account issue solution, so that we can pass through it further. And this step will be focused just on user conversations and database exploration. No modifications are allowed here. Then I can actually write code based on that. If successful is true, I'm passing the original solution to the finish step. That's when I finish and stop my agent. Otherwise, I'm passing the feedback to the next step to adjust. And then coming back with a new, updated account issue solution. Please note that it's not possible to exit this loop before successful is true. This workflow is much more reliable than anything we have built so far before. So now let's learn how to develop that. Well, let's code the strategy. For that, let's understand how to build this basic component using the domain modeling approach, the subtask. For that, I'm going to use the subgraph with task out-of-the-box component from Koog. That requires the input class, the output class. I'm just declaring what I want, just the class. List of tools. And optionally, I can even switch the model on the fly during the subtask. So each subtask might have separate model suitable for this specific step. And then I'm explaining how to create the input, like what the prompt for the model, what's the task. So in this case, for example, identify the problem. That's the description of the task, right? It's a string. And that's how you do it. Now we can actually build a workflow. Identify problem. It's a subgraph with task from string to account issue summary with a limited set of tools. And I'm using GPT-5 model because in my experience, GPT are a little bit better when it comes to user conversations. Next step, fixing problem, same component, different types, different tools, and also different models. I'm switching to Sonnet on a fly, and this step will be working with Sonnet because, well, again, in my experience, it's a little bit more precise when it comes to tool calling, and here we need to do a lot of database modifications. Next one, verify solution, almost the same, just a little bit different component. It's called subgraph with verification. It's also out-of-the-box component, and it just makes sure that the critic result and the final LLM judgment is performed before LLM exits this step. And also, well, I'm using GPT-03 model. Why? Because we need a reasoning model here. We need to reason about the output. So I'm switching the model on the fly again. Last but not least, adjustment step, same component, different types, different tools, different model, different task. That's it. What's left? Just to glue all of that together. For that, I'm going to define the edges for my graph. First 3 edges are pretty primitive, from node forward to node. The other ones, though, they need some branching here, so let's define that. Verify solution forwards to node finish on condition it is successful. But that one will not compile, because verify solution provides a critic result class. Finish step expects the final solution, and critic result is not a solution. So I will have to transform the type on a fly while going through this edge. For that, I'm going to write transformed to the input. Same way, and yeah, it's all compile time checked. You will not be able to deliver such agent that is not type safe, right? So, and then the same way, the other edge, verify solution forwards to adjustment step on condition it is not successful, transformed to a feedback. Why? Because adjustment step requires a string. and the edge back the same way. And that's it. And please note that I never said anything about message history or the context management, because all of that happens out of the box under the hood. Moreover, you don't even have to care about how you explain what was before with the new model, with the previous model, to the next one, because Koog does that also out of the box. I can illustrate that. Remember, identify problem was working on the GPT model, and it has the access to conversation tools and reading tools. The next step, fixing problem, was working with the Sonnet. Reading tools are still there, but the problem is that conversation tools are no longer available, but they are already in the message history. So if you just copy the message history and continue from there, lots of models would just break. To solve this problem, we automatically re-explain the model, like the tool calls to the model, either with a plain text or JSON, or you can also customize just an interface. You can inherit how you describe unexisting tool calls to the next model. But it's just going to work with the default solution, so you don't have to even know about that. And that's when fixing problem continues with other tool calls and goes further. That's how it works. Moreover, of course, sometimes you need some custom actions, not just LLM subgraphs or loops. You have to be able to put some actions and guardrails. That's pretty easy. You can define custom node from any type to any other type. Here I'm defining the ask user confirmation node that just asks something from the user and comes back with a typed user response. You can send SSE event, you can show some UI message and ask the user to fill in the form and then come back to the LLM with the form filled, or you can do anything inside. You can put some guardrails and checks. And that's very much recommended. And that's exactly what Mercedes-Benz has done. You have already heard the quote from the keynote, right? But graphs are not the silver bullet, and we do understand that. And Koog comes with different types of strategies. So of course, you can start always with the basic strategy, the simple loop. You can also develop graph-based strategies, and that's what we recommend. But you can also develop functional strategies, almost in plain code. Indeed, all these edges and conditions and transformations can be expressed with just Kotlin. For, if, while, that's it. The only problem is that you're going to miss some observability and persistence. I'm going to talk about it. But it's a good start. You can prototype and write functional strategy fully in Kotlin, still with most of the Koog's features available and supported, including the automatic context management. But before deploying to production, just refactor it once to a graph strategy, and that's it. You can also use multi-agentic systems and build planner-based strategies. Who ever heard of GOAP, Goal-Oriented Action Planner? OK, just a few people. I'll explain. So functional strategies, again, as I said, support most of the things from Koog. You can code with normal Kotlin, no persistence, and no observability. Planner strategies, this is a pretty novel approach, originally pioneered by Rod Johnson. And the approach comes from gaming. So essentially, you just define the nodes, or like the actions. And then you also describe the preconditions and beliefs, like what has to be true before the node is executed, and what's the belief or side effect of the node. And then the planner will plan the optimal path and replan if needed. So it's more dynamic, and it can kind of draw the edges for you. And you can also do that in Koog. I'm not going to dive too deep into that. So we have just developed a custom strategy that is so great, so good, and so resilient. Any problems? Well, problem number 2, runtime crashes. What if your agent just crashes in the middle? Well, LLMs take time. User conversation and tool calls take even more time. What if user comes back with an email response the next day or the next year? So suddenly, your JVM might crash, or if you're using AWS EC2 spot instances for obvious cost optimization reasons, well, your Amazon provider might just preempt your instance and rerun your process from another machine. And you will lose all your progress and all your money you paid for LLMs because you have to start from the beginning. Moreover, you can start from the inconsistent state of the database, just in the middle of the execution. Not a good idea to deploy such system into production. And there is a solution. It's called Koog's persistence. You just install it to your agent, any agent, but it has to be a graph one. Why? Because it's not possible to persist any place of the execution just in the middle of your Kotlin code. You cannot serialize Kotlin function and just rerun from there. But you can do that with graphs, because there is a structure. You only need to provide the storage, where to store the endpoint, S3, database, file system, memory, somewhere. And enable automatic persistence so that it will checkpoint after each step. So how it will work? Well, it will just checkpoint the exact node of the workflow, plus the state, including the message history, storage, meta information, everything. Let's just illustrate that. Let's zoom in, and zoom in again. Let's imagine that our agent is somewhere inside this verify solution step. For example, calling LLM, or doing any other inner atomic action. It's also a node. So what will happen is Koog will checkpoint the place of the algorithm, the node, and also all of the meta information, including the system messages. And by the way, there is a to-do. Why? Because you never finish your presentation in time. I'm joking. What will happen is the same agent will recover after a crash, exactly from where it stopped. You only need to connect with a storage provider. Persistence storage provider with JDBC is supported. Exposed is supported. Many databases are also supported. And you just connect to the storage provider, and it will just work. Moreover, you can also do it with Spring. You can use Spring Data Source or Spring AI or Spring Boot, whatever you want, and the bin will be just injected, and you can use it here. So, next, you cannot just proceed without debugging and monitoring. No system is perfect. You have to observe what's happening. For that, we're going to integrate with observability tools. Here, I'm installing OpenTelemetry. It's also a feature in Koog. You just install it to any agent. And you can connect it to any span exporters and span processors if you already have some OpenTelemetry compatible tooling in your system. Or if not, we can also use Langfuse integration. Langfuse is pretty popular AI observability specialized provider. There is out-of-the-box integration. Just provide the credentials to your Langfuse console, open it, and you will see all the graph nodes, how much money you spent, messages, tool calls, tool responses, all of that. Same way you can integrate with Weights and Biases Weave, another pretty popular tool. Just add the Weave credentials, and you can see the same exact information in Weave console. Or the Datadog, same thing. But there is one more problem that I promised to solve, which we all, I hope, love, which is money. Agents have to be cost efficient. So the first problem is pretty obvious. Well, long-running agents take a lot of money from you. For instance, we've been trying and running and evaluating different coding agents in JetBrains. And the thing is, one single run through the whole SVE benchmark costs around several hundreds of dollars, like $500 to $700, just one single iteration over the whole benchmark. And that can come with a lot of cost, because if you deploy such agent for millions of users, not in the IDE, but on the backend, that's going to be very expensive. Moreover, LLM will have to read the whole history of the conversation from the very beginning in order to come back with every single next message, whether it's an assistant message or a tool call. It will have to read the whole history of the tool calls and conversations in order to guess the next action. Obviously, it's very expensive. Moreover, the more messages are in this book of history that the model has to read, the worse it works. Precision drops drastically. Moreover, latency increases. You have to wait longer and longer and longer times before you get each next message. But that's not the only problem. Moreover, you can easily hit the context limit. That's especially true if you're running on local models, like on device, or if you're just deploying smaller llamas. But even with the frontier models, I once made a personal agent just for myself. I used a frontier model from popular provider, which has 2 billion token context limit, which is the largest available today. And I asked it to perform a very simple task. You know, just look through my documents. Here is my passport, 40 PDF pages. Here is my job contract, 72 pages, and some other documents. Well, pretty simple task. And I asked, like, please check, do I have all the required documents for the UK visa? I was applying for the visa at that time. And after several of iterations reading through my documents, it just crashed with an exception. Sorry, I hit the context limit. Imagine scaling the same agent for millions of users on your backend if it cannot solve small problem for just me, a single person. That's not going to scale. And you have to solve this problem, and there is a solution. It's called history compression. So it's also a node in the graph workflow. It's called node LLM compress history, and it has just one type, because it doesn't do anything with the value. It just passes it further. But what it does, it actually composes a TLDR message. Instead of the whole history, LLM will just see a TLDR, what has been done before this point in time. And you can, of course, put it anywhere in your strategy. For example, between adjustment step and verify solution step, if the history is too long, I'm putting the compress history node. And that's how I do it. So adjustment solution goes to compress history on condition history is too long, and it goes to just verify solution if it's not too long. That's it. Yeah, and history is too long is just an extension method that you can define. If the token usage is huge, that's it. The problem is this. Now LLM doesn't have enough information to come back with the right decision. And we also tested that and hit into that problem. For example, if you are doing coding agent or banking agent, and the agent has already explored the repository or the user account, and then you compress the history, of course, it will get the TLDR. But it will lose important information about, for example, project dependencies or some transactions throughout your account. And what it will do next? In the next step, it will start to explore your system again from the beginning. And you wanted to save money, but you will actually lose money because it will cost you more tokens. Of course, we know about this problem, and we also solved it as well, because we came up with different strategies for history compression that you now also can use. The first one that we tried was chunking. Inside this history compression node, there is an optional parameter called strategy. And there is a bunch of out-of-the-box strategies that you can use. And it's also an interface you can implement your own if you want. So chunking is pretty simple. Here, I'm just asking the model to chop the history into pieces of 20, compress each of them independently, and then instead of reading the whole book, LLM will read the plot of the conversation. Works much better, but still not good enough. And the final thing that we came up with was fact retrieval. And by the way, these strategies are not available in any other frameworks, including Python frameworks. So it's only in Koog. So fact retrieval works like that. As a developer, you can specify the concepts of what specific things you want to persist in the history. Like here in our banking assistant, I'm asking to save the steps that were important and also the banking operations that were suspicious. And you can also come up with your own list. So instead of just blindly persisting the plot, it will search for the specific facts, drop the history, and then compose a new one that naturally mentions these facts. And this strategy works pretty well, and it gained us around like 5 to 8% improvement on the benchmark. So that's the illustration. Instead of reading the whole book, LLM will be left with just a few important pieces of paper on the table. You can also scan the QR code to view the full example that we just cooked. Gonna just leave this slide for a while. And just to recap, so we started with a simple agent today. We programmed tools in Kotlin. We connected to Spring application. We added sessions with chat memory. We also tailored specific strategy for our task using graph strategy to get the most reliability and control. We enabled fault recovery with persistence feature. We connected to different observability tools. And we cost optimized our agents using history compression. Here's the website for Koog. If you have never visited it, please feel free. And, of course, try Koog 1.0 today and cook your production AI tomorrow. Thank you so much for your attention.